Now for our final lecture on stars, as we talk about their death and the corpses they leave behind. Let's first discuss the fate of stars that are smaller in mass, stars the size of the Sun, roughly, or a little bit smaller or larger. For a star like the Sun, it can burn hydrogen for about 10 billion years. But eventually it runs out of hydrogen to fuse in its core, and it becomes a bloated red giant, fusing hydrogen in its shell only. Eventually, there will be what's called a helium flash, and helium will start fusing in the core when the Sun will end up in the yellow giant phase. Now, incidentally, the main sequence lifespan of the star like the Sun, it was 10 billion years, but the red giant phase, it goes through that shell burning phase in only 1 billion years. So that's only a tenth of the time it takes before that shell is exhausted. And then when it starts burning helium, it can only do so for an even shorter amount of time, 100 million years. Eventually it will run out of helium to fuse, and at that point it's the end of the road for the star. It will eventually cool, and its outer layers will be ejected and float away in what's called a planetary nebula, leaving behind at the center the corpse of the star, or the white dwarf. So here's a snapshot of the tracks of the lifespan of a star like our Sun. Starting out in the proto-star phase, eventually it enters ZAM's zero-age main sequence when it lands on the main sequence. It will stay there on the main sequence for about 10 billion years, and then it will enter the red giant phase towards the upper right part of the HR diagram, followed by the yellow giant phase when it is burning helium, and then after that is going to cool and eject its outer layers and become a planetary nebula surrounding a white dwarf. So as the red giant expands, it cools. This is why, in fact, its color changes, because the cooler the surface temperature, the redder the color. We know that from Wien's law. And whenever it runs out of fuel entirely to fuse, then the outer layers will be expelled and form this planetary nebula. It's called a planetary nebula, but don't be confused. A planetary nebula really has nothing to do with planet formation. It's just kind of almost a misnomer in terminology. When I think it was first dubbed, it wasn't really known what this was or what stage of a star's life it represented. It is now known that this is the end of the lifespan of the star, so it doesn't have anything to do with the formation of planets around the star. Nevertheless, it's called a planetary nebula, and here's an example of an hourglass nebula, which is a planetary nebula that was sort of interesting because it didn't just form one single circle like you see depicted here on the bottom right, but almost like two, or a figure 8 type shape. And what's left behind in the center of the planetary nebula is the white dwarf star. And this is like a stellar corpse. Think of it as a very hot cinder left behind after a glowing inferno has been put out. The cinder can last a long time. It's very hot, 25,000 Kelvin, and it only cools slowly. It's not got any heat from fusion reactions. It's just glowing from the leftover heat of the intense core of the star. These white dwarf stars cool so slowly that in fact none of them have entirely cooled to the point of becoming a black dwarf star, but theoretically they ought to become dimmer and dimmer as they cool until they're just a dark, inert sphere left behind, which would be called a black dwarf. But in the age of the universe, there still hasn't been enough time for a white dwarf star to cool to that point. So we don't actually observe black dwarf stars. They would also be difficult to see. But theoretically, that is what would happen to the white dwarf star over a long period of time. So what happens if a white dwarf star exists in a binary system? As you can imagine, if you're in a binary star system, both stars are not going to generally die at the exact same time. So maybe perhaps one goes through its final evolutionary stages, ejects its outer layers, and leaves a white dwarf star behind. But perhaps its companion star in the binary pair is still hanging on to the last fusion burning phases of its life and is in a close orbit to this white dwarf star. If they are close enough in orbit to each other, then mass from the companion star as it swells to a giant phase can get so close as to become gravitationally attracted to the white dwarf, and this matter will then accrete onto the white dwarf star. If enough matter accretes onto the white dwarf star, there's an intense explosion that can occur from the dense hot material on the surface of this white dwarf star. So if this explosion occurs on the surface of the star, this is what we call a nova. Sometimes in a binary system, this will happen again and again as the giant star companion is going through its final stages of life. The white dwarf star will accrete matter, explode it away, and then start accreting matter again and explode it away, and so on until eventually the companion star dies as well. Here are some images of what it looks like after a nova. Reminds us a little bit of a planetary nebula. But this is a more violent process that takes place. And an even more violent process can take place if even more matter is accumulated by the white dwarf before it gets a chance to explode it off in a nova. If the matter is accumulated rapidly and ends up exceeding about almost 1.5 times the mass of the sun, if it reaches that point, it can't really explode on the surface the way a nova would. Instead, there's so much compression and gravity squeezing that the star itself, along with the outer accreted material, explode together into nothingness, destroying the white dwarf in this case. So when that happens, this really violent explosion is called a type 1a supernova. So we tend to think of supernova as the deaths of stars, but a type 1a supernova is actually the death of kind of a stellar corpse rather than a fusion burning star in its own right. But there are other types of supernova that do involve the death of fusion burning stars. However, this type 1a supernova is interesting because it is exceedingly bright, first of all. In the bottom right-hand corner of the slide, you see that it is so bright that if we look at a distant galaxy, we actually can make out that individual star that is exploding. Generally, when you're looking at a distant galaxy, you cannot resolve individual stars. However, during a supernova type 1a event, you can make out where that one individual star is taking place and measure its brightness relative to the brightness of the galaxy that it exists in. And if you do that, it turns out that type 1a supernovae all have similar peak luminosities. So if you catch it just when it happens, which is becoming easier and easier to do, then you can basically figure out what its brightness looks like to you. And since you know that it has almost a very predictable luminosity, inherent luminosity, then based on how bright it appears to you compared to how luminous you know it actually is, then you can figure out how far away that galaxy really is. So this is another example of what we call a standard candle that helps us measure the distances to nearby galaxies. And so speaking of more violent deaths, let's look at the death of more massive stars than the Sun. If you're looking at a massive star, say 25 times the mass of the Sun, it can exist on the main sequence for really only about less than 7 million years. At that point, it's going to start expanding into a blue supergiant, which has the hydrogen shell fusion taking place, just like the final stages of the Sun. That will last you another 7 million years. So we still haven't even made it to 1 billion years here. But eventually, then you have this helium core fusion reactions taking place, again like the Sun in its final stages, but much shorter lived. And eventually this star will swell to a red supergiant, where it will go through a series of final fusion reactions before finally exploding as a supernova, a core collapse supernova, which is a little bit different from a type 1a supernova. And then what's left behind will be a neutron star. So after the helium burning phase, our Sun stops at that. It cannot attain enough pressure and heat in its core to burn any heavier elements. However, a more massive star can, because it has more pressure and more heat in its core due to the extra mass that it has compared to our Sun. This allows the star to burn carbon and then heavier elements still, leaving its what we call ash behind in a layer that resembles sort of an onion-like structure. This is what the interior core of a star would look like, a massive star towards the end of its life, where you would have hydrogen in the outermost shell. The ash of that is helium, which it's still trying to fuse, leaving behind an ash of carbon, which is fusing into neon, which is fusing into oxygen, which is fusing into silicon, which is fusing into iron at the core. The heavier elements, of course, do sink to the center, just how we talked about differentiation. That makes sense that the heavier elements would be in the center. But once you have iron in your core, this is the end of the road for this star. It is actually impossible to fuse iron and gain energy out of it. Instead of it gaining you energy, it loses you energy. So that's the final stage for the star. But here's a summary of all those stages that it goes through, where it's burning hydrogen, then helium, then carbon, neon, oxygen, and silicon. And what's really interesting is if you look at not only the minimum temperature required for these fusion reactions, which is really tremendously hot, but also the duration of how long these different fuels last the star. Remember that we only had about 7 million years to start with the hydrogen fusion, and then we only have 700,000 years for helium, plus about 300 years for this alpha capture. The rest of the carbon fusion is taking place in only a matter of 8 months, so less than a year. It burns through all of the carbon that it had. And in less than and then in 3 months, it burns through all the neon that it has to burn. And its oxygen fusion reaction only takes a day to go through. So when you get towards the end, then basically the iron core is when the supernova event is imminent. And so the interesting thing also, aside from the way that this onion-like structure produces different elements, is that even more elements are produced in the supernova explosion itself. All of the heavier elements in the universe were created from supernova explosion of stars. So it was unknown for a long time where these different elements came from, and it was debated whether or not they were there from the start of the universe or whether they were somehow produced in stars. And so, oops, I'm getting ahead of myself here. And so some people were saying, no, look, this is how much there was in the universe to start with, and other people said, no, I think the universe is in a steady state and all the elements we know of were created in stars themselves. And it turned out that both of those people were partly true or partly correct. Those who championed the idea of primordial distribution of elements were correct in that the universe was born with about 3/4 hydrogen and about 1/4 helium. But then all of the smaller, what makes up the rest of the elements is a smaller proportion. So that's why I'm saying about 3/4 and 1/4. Clearly it's not entirely that. There are other elements, but all of those other elements were created in this supernova explosion. And a core collapse supernova explosion looks similar to this type 1A that we talked about earlier, but it's a little bit different, as you see. And so we have different type names for them. Basically, anything, there's type 1A, type 1B, type 1C, and type 2 supernovae. Anything farther in the alphabet than A, or larger than 1, is a core collapse supernova. So type 1A is the exception. That is when a white dwarf obliterates, that we talked about earlier, from being in a binary system. But type 2 supernovae and also type 1B and C, which are rarer, are the result of a core collapse supernova of a fusion burning massive star. So what does this explosion leave behind? It leaves behind not a white dwarf, but a neutron star. And sometimes if the neutron star is massive enough, it can then collapse into a black hole. However, if there's enough mass to start with and a very violent explosion takes place, it may skip that neutron star phase altogether, going directly into a black hole as the corpse. That would be what we call a hypernova. So in this core collapse, there are jets that spew material and radiation in the poles of the stellar corpse, such as a black hole. But this can also happen with a neutron star. And so one puzzle was that some stars that we saw we didn't know they were neutron stars, exhibited a pulse, in that it was a periodic intensity fluctuation, almost like a heartbeat, because it happened pretty rapidly. And, at first we thought, well, since it's so regular, maybe this indicates some kind of crazy alien civilization. But actually, no, there is a natural explanation for this. And so this is when Occam's razor tells you to go with the simplest explanation. Instead of an alien civilization, we don't need to posit that. Instead, we think about what happens with a neutron star. And if those jets are aligned in such a way that during its rotation, it shines on us and then shines away, and then shines on us and then shines away, similar to how a lighthouse might work, then you're going to see these periodic brightness spikes that are observed. And so this makes sense. These kind of neutron stars we call pulsars. Pulsars can slow down over time. Generally, they can be pretty regular, but we can measure some slowing down if we are observing them over time. And so that leaves the only other stellar corpse that can be, which is a black hole. And black holes are a little bit difficult to understand without understanding a little bit about the speed of light and this idea of escape velocity. The escape velocity for any object in space follows the equation you see here, which is that the square root of 2 times the universal gravitational constant times the mass of the object divided by the radius is what it takes to escape from that object. You need to be going at least that fast in order to escape. So if you plug in the Earth's mass and the Earth's radius, you would find how fast you need to get your, say, spaceship to go in order to actually leave and escape the Earth. Other objects that are more massive and smaller in radius are going to have a greater escape velocity. So these very dense stellar corpses have tremendously large escape velocities. A white dwarf's star's escape velocity, for example, is 6,000 kilometers per second, which is 10 times faster than what it would take to escape from the sun. And so you can imagine if we get more massive and smaller in radius, and as this stellar corpse is compressed and gaining mass, then we can get to a point where that escape velocity would equal the speed of light, which is 3 times 10 to the 8 meters per second. If it reaches that particular escape velocity, then what we're saying is that nothing can possibly escape because nothing can go faster than the speed of light. Even light cannot escape that object, which is why it's called a black hole, because even light can't escape. There's no light given off. It is trapped inside. You can also think of a black hole as a warping of space-time so that the indentation is so large, kind of like the funnel at the top left of this slide, that even light cannot escape that indentation. Because of this warping of space, then sometimes you have strange effects occur, such as gravitational lensing effects, but basically the idea is that nothing can escape from this severe indentation from the corpse itself, so that it is dark, it is black, it is a black hole. It kind of looks like a hole if you think about it in terms of how it warps space. So if not even light can escape, then how are we going to ever hope to see a black hole? Well, black holes can accrete disks in a binary system similar to how the white dwarf star could. And so this accretion disk gives off intense radiation in the X-ray region as the material spirals in to the point of heating up and emitting this X-ray radiation as it plummets into the black hole. So when we observe a periodic X-ray burst and then nothing, an X-ray burst, etc., that could indicate a companion star orbiting a black hole. Now, incidentally, these are not the only kind of black holes that can form. We can also have supermassive black holes, which are thought to exist at the center of pretty much all galaxies. Those are formed in different ways from how these black holes are formed. These are stellar-sized black holes. So let's talk for a moment about star clusters. When we talked about the birth of stars, we discussed how generally there's a large cloud of gas and dust that the star forms out of. Oftentimes, the cloud is so large in extent that associations of stars are pretty much born together out of the same cloud of gas and dust. Depending on how many of them there are, we can call them different things. We can call them an open cluster if there's just a few of them and they're far enough apart we can kind of see the space between them. The Pleiades is a famous example of an open cluster. Eventually these will probably spread out into what are called associations. But more densely packed clusters are called globular clusters, and globular clusters are many stars that were all formed out of a huge cloud of gas and dust. And so since they are born together, you can think of them as twins or triplets. They're all born at the same time, pretty much. Then we can do an interesting thing with these globular clusters. Specifically, we can tell how long ago the globular clusters formed. How can we do this? Well, what we do is we observe what kind of stars are present in the globular cluster and we plot them on an HR diagram. So on the Hertzsprung-Russell diagram, we might notice that most of the stars are along the main sequence, but pretty much most of the stars beyond a certain mass or certain luminosity class have evolved off of the main sequence. So since they were all born at the same time, then what this means is that the stars that are on the main sequence have not had enough time yet to evolve off of the main sequence, but just where those stars start to evolve off of the main sequence based on the known lifespan of a star like that, then that must be how old the stellar cluster or the globular cluster is, because those are where we start seeing the stars evolve. They were born at the same time, so they've all pretty much lived up until that point that we know those particular stars start to turn off of the main sequence, evolving upwards to the giant region. We call this the turnoff point. Based on that turnoff point, then we can figure out what the age of the cluster is. So for some examples to kind of illustrate this, if we had a very young cluster, globular cluster, then pretty much everybody would be on the main sequence except those very low mass stars that are still in the process of forming, because remember, they take a very long time to actually form and reach ZAM, zero age main sequence. So they haven't yet gotten to the main sequence. They aren't truly yet stars. A young cluster that isn't quite as much in its infancy would have basically all of the stars on the main sequence. An older cluster might have most of the stars on the main sequence, and the turnoff point may be where the higher mass stars are, and so we can deduce that this cluster must be that old, that these stars that burn for millions of years are now starting to evolve. So maybe the cluster is now millions of years old based on the lifespan that we know these very massive stars have. An even older cluster might have a turnoff point near our sun. And at that point, then we can deduce that, wow, well, if all the stars more massive than the sun are evolving off of the main sequence, and the only ones that are still on the main sequence are smaller mass than the sun, then this cluster must be billions of years old for all of these stars to have already had time to evolve off of here. And a really, really old globular cluster would consist almost entirely of the giant stars, the evolved stars, and then the only thing left on the main sequence would be your longer-lived small mass stars, very small mass stars.